Hi, everyone. My name is Nikita. I'm production engineer at Facebook network team. And my talk is going to be about our layer 4 load balancing infrastructure. So today we're going to talk about motivation. Why do we need this additional layer of load balancing? We're going to talk about possible implementations, pros and cons of different solutions. I'll talk about how we're doing this at Facebook, what we are doing today, what we have been doing before. And I will talk about how the future could look like. But before we start, there is a few terms which I'm using a lot during this presentation, so I want to describe them in more details. The first one is layer 7 load balancer. This is network device which terminates transport session. It's usually application aware, so it can do load balancing based on the application data. For example, HTTP headers. The second term is layer 4 load balancer. This is, again, the network device, but it's application agnostic. So it can do load balancing only based on the fields from IP packet itself. And the last term is 5-tuple. This is basically how you can describe the flow inside your network. This is 5 fields from the packet, which stays the same for every packet in the same flow. And these fields are source destination IP addresses, source destination port, and protocol number. So let's start. Why do we need this layer 4 load balancing? To be able to answer this question, first of all, I want to describe how layer 7 load balancing architecture looks like and what the pain points there. So you have layer 7 load balancer. Here at Facebook, we're running Proxygen. If you think about any other open source solution, this is Nginx, Varnish, Haproxy. And usually the way it works, it have pre-established TCP or transport connections to the backends. And when it receives the request from the user, it terminates this request doing the decryption. And then based on the application data, send this request to one backend server or another. But as you can see, from this picture, this Proxygen, this is single point of failure. So what here at Facebook we don't want to have is that when user hit the Proxygen, Proxygen just disappears. Could be a software maintenance, software update, power issue. It just could run out of the CPU. And the question is how to make this scale. So how to make topology like this works. And the first possible approach is to use DNS and for the load balancing. In that case, each of the Proxygen will need to run public IP address. And for the request for the facebook.com, we need to craft the reply in a way that it will contain all the IP addresses of all the Proxygens. And client will just pick one of them and initiate the transfer connection. The drawback of this approach is that DNS response is limited in the size, so you cannot scale out indefinitely. And the second issue is, as soon as your DNS response became bigger than DNS request, suddenly your DNS infrastructure became attractive for the people who are using DNS amplification type of attacks. The second possible solution is doing something smarter on the DNS server side. So for each request, you reply with the single IP address of the Proxygen, but for different users, these IP addresses are going to be different. So the issue with DNS response time just go away, or response size just go away. The pros of DNS-based approach is that it's super simple. You don't need to change anything inside your network. All the changes has been done on the DNS server side. The cons is that DNS is super slow when it needs to react to any type of changes. Just to show you as an example, here we have one of our H cluster, and we needed to do maintenance there. So what we have done, we initiated the drain procedure, and that means that for the request for the facebook.com, we stopped to reply with IP addresses from this H cluster. And for facebook.com, we have DNS ETL of 1 minute. So we started the drain, and if that was an ideal world, after 1 minute, there won't be any connections there, but reality kicks in. After 10 minutes, half of the users who have been using this H cluster before still using this cluster. After 30 minutes, 20% still was routing there. So in that case, that was planning maintenance. So Proxygens was up and running and were able to reply to the user request. But if that was, for example, power outage, this is basically for how long you are going to black hole traffic. The second possible implementation is to use network for the load balancing. Basically, to run, to leverage ECMP, and ECMP stands for equal cost multipath. In that case, we'll need to run dynamic routing protocol on the Proxygen side. This is BGP in our case. All of the Proxygens advertise the same IP address of the service. And if you ever heard the term TCP anycast, this is basically what it is. And this is example on the packet rate for the ingress side on the Proxygen level. And as you can see, ECMP more or less works. Each of the Proxygen receives equal amount of packets per second. So pros of this approach is this is super easy to scale out. You just like start new Proxygen, start BGP there, it starts to advertise IP address of your service, and it starts to attract traffic almost immediately. The cons are that ECMP stands for equal cost. So you cannot have unequal load balancing. And that basically means that you cannot run different generation of the hardware inside your edge cluster. Because either the old generation will be overutilized or the new generation is going to be underutilized. The second issue, and this is the biggest one, if there is some event, for example, one Proxygen goes up or one of them goes down, you will see massive rehashing on the networking side. And just to show you how big this issue is, first of all, I want to talk about how ECMP works on the networking gear. So usually, networking gear take the hash of 5 tuple and divide this by the number of the next hops toward this destination. And the resulting number is the index of the next hop, which is going to be used for this flow. So let's imagine a situation when we have 5 Proxygens, and the hash ring for this will look like something like this. Basically, these pictures show you that for the hash value equal to 1, the flow is going to be steered to the Proxygen number 1. For the hash value equals to 7, it will be steered to the Proxygen number 2, etc. So now let's imagine that one of the Proxygen goes down. And suddenly, the formula became something like this. So let's look how many flows are going to end up on the different Proxygen after this event. And the red square shows the amount of flows which are going to be affected. That basically means that these flows are going to be steered to the different Proxygen, which have never seen any packets from this flow before. And if we are talking about TCP, the Proxygen will just reply with TCP reset. And depends on the client implementation, either client going to be forced to reconnect to your edge cluster or will just see 500s. So from this example, it's easy to show that 80% of the flows are going to be affected, which is not great. And now we are going to the third approach, and this is what we are doing here at Facebook. So inside your network, in front of the Proxygen, you'll have additional layer of the networking device. This is layer 4 load balancer. And inside the Facebook, the code name for this is Shift. And the idea is that Shift receives the traffic from the network and resend this traffic toward the Proxygen. And by receiving traffic from the network, it gets all the benefits of the ECMP. But because it's more sophisticated than typical networking gear, it can solve all the ECMP pain points, such as unequal load balancing or massive rehashing. So as we have seen before, ECMP usually works. This is network to shift side of the connection. Now let's look how the shift to Proxygen looks like. So in this example, 2 of the Proxygens are running special type of software, and they need to receive less traffic than the rest of the fleet. So with Shift, we can easily do that because it can support unequal load balancing. Or, for example, this is another edge cluster where we have like different generation of hardware, and we can operate this without any issue. So when you will think about how the packet on the wire looks like, when we send the network send traffic to the Shift, this is just native IP. But when Shift send traffic to the Proxygen, we are doing IP and IP encapsulation. So this removes the requirement for Shift and Proxygen to be in the same layer 2 domain compared to other solutions which are on the market. And because we don't have this limitation, this allows us to build our edge network in a close-based topology. So there is few interesting ideas built in our layer-4 load balancer. One of them is that using consistent hashing. So the way Schiff pick up the backend is that Schiff receives the traffic. It look into 5 tuple, calculate the hash value from this 5 tuple, and by comparing this resulting number to its configuration, it sends this flow to one proxygen or another. So it sends traffic to the proxygen receives the packet from this flow, and the session to the user has been initiated. Now let's imagine the situation when, for example, we need to do software upgrade on the Schiff side, or do some kind of maintenance, or it's just was power issue. So Schiff went down. Or, for example, from the previous picture, in close-based topology, for example, we need to do software maintenance on the span layer switch. And no matter what had happened, both of these events are going to trigger massive rehashing on the networking side, and the next packet in the same flow will end up on the different Schiff. But because to pick up the backend, we are using only data from the IP packet itself, this 5 tuple, it's the same. So this different Schiff runs the same algorithm, and this flow will end up on the same proxygen as before. So all these events are going to be transparent from the end user's point of view. And this gives us a huge benefit that we don't need to share the state between different Schiffs, because the state is basically encoded into IP packet itself. The second approach is the way we are doing service maintenance. So basically, Schiff in day-to-day work could operate in stateless mode, but it still have stateful table inside. And the whole purpose of this stateful table is for us to be able to do the service maintenance. So for example, Schiff received the packet from the user, send it to the proxygen. Now we have decided that we need to do the software upgrade on the proxygen side. So we drain this proxygen, and basically that means that this proxygen signals to the Schiff that it doesn't want to receive any new connections, but it still wants to receive the packets from already established ones. So if the Schiff will receive packet for the new flow, it will go somewhere else. But if Schiff will receive the packet from existing flow, because of this stateful table, this packet is going to be routed to the proper proxygen. And another interesting approach is how we're handling ICMP destination unreachable messages. So why do we need this? Sometimes we could end up in a situation when proxygen replied to the user with a packet of the big size, but somehow ISP's gear have smaller MTU on the last mile, and surprise, it decided to honor DF bit inside IP packet. So in that case, the ISP's router are going to create ICMP destination unreachable message, and the way it's implemented that it will have source IP address as IP address of the router. The destination IP address is going to be IP address of the service. And inside ICMP as a payload, it will have initial headers of the packet which have triggered this ICMP message. So this ICMP message is going to be received by the Schiff. And some other solutions, what they are usually doing, they are just replicating this ICMP message across all of the layer zone balancers inside the edge cluster. But what we're doing here at Facebook, we have all the data what we need. So we look into ICMP payload. We see the headers from the initial packet, running the same algorithm as before, and after that we know to which exactly proxygen we need to send this traffic. So this is interesting. So the previous slides was more or less about generic architecture. Now let's talk about how the forwarding plane has been involved inside the Facebook. So original version of our load balancer was based on the IPVS model from the Linux kernel. It was working great for us for, I think, almost 5 years. But what we have seen in the last years is that when the load increased, it became CPU-intensive task to run this IPVS model. So because it was heavy on terms of CPU usage, we wasn't able to collocate any other CPU-intensive task on the same box. The second issue is that, like a couple of slides back, I was talking about the stateful table. It works great if you have like just a regular traffic pattern, but when something starts to trigger a lot of new flow state creation, the performance goes really down. So for example, if you see something like TCP syncflood, that box wasn't behave as expected. And the last issue was that IPVS is a part of the Linux kernel. So if you need to add something new there, basically you're kind of forced to install the new kernel and restart the server, which could take time and not fun to do. And because of all these limitations, we were kind of forced to run Shift on the dedicated boxes inside our edge network. The rough number is something like Shift was running on the 10% of the servers inside edge cluster, and the rest was the Proxygen. So sometimes last year, we have decided to completely rewrite our forwarding plane, and we have started to use BPF and XDP technologies. BPF is in kernel virtual machine, and XDP is a super fast packet processing facility. So what this gave to us is that our forwarding plane became CPU efficient, but because XDP is still the part of the Linux kernel, it works really great with the kernel's TCP IP stack. And the last benefit is that BPF is in kernel virtual machine. So the way it works is that from the user space, you upload the bytecode into this VM, and it runs code on your behalf. So if you need new feature, you just like re-upload this code, and you don't need to do any restarts or things like that. So super fast and CPU efficient. So let's see how efficient it was. In one of our edge cluster, we started to run the canary, which was based on this new XDP-based forwarding plane. To compare with, we have like other boxes which were running IPVS. So IPVS was receiving some amount of packets per second. Into this new XDP-based forwarding plane, we started to send 3 times more traffic in terms of packet per second. And then we started to look into CPU consumption. And to compare with, one of the boxes inside this edge cluster was idling. Basically, it wasn't doing any CPU-intensive task. And we were using this box as a baseline. So let's look. We can see like how many CPU consumption idle box had. This is how many CPU IPVS was using. And this is how much XDP was using. So this picture shows us that XDP was receiving 3 times more traffic, but CPU consumption was 7 times less compared to the IPVS. So that was really great. So another benefit is that XDP works really great with kernel's TCP IP stack. And when someone wants to write some fast packet processing software inside the Linux, usually they are using some kind of kernel bypass technologies, such as DPDK. But the issue with DPDK is that it works really great for your application, which has been written with DPDK in mind. But if you're running any other application inside the same server, this application will suffer. So let's compare XDP with kernel bypass technology. So usually the way kernel bypass works is that you receive the traffic on the network interface card. You send this traffic to your kernel bypass application, for example, load balancers forwarding plane. It's 0 copies, so it's fast and efficient. If the destination was the application, it's doing packet processing and send traffic back. Everything works super fast and CPU efficient. Now let's imagine this. We have this situation where we need to send traffic to another application which is running on this same box and which are not DBTK aware, for example. So again, send the traffic to the forwarding plane. Forwarding plane figure out that this traffic needs to be, this packet needs to be sent to the kernel. So it sends packet to the kernel. And each time you cross the user space and kernel space line, there is packet copy involved. So forwarding plane writes to the kernel writes to the application reply to the kernel. And now, because kernel doesn't really work with the physical interface, it loses all the benefits of the hardware offloads which are built into modern network interface cards, such as TCP segmentation offloading or transmit checksumming. So kernel writes back to the forwarding plane, and forwarding plane writes to the wire. Now let's compare how XDP works. So again, NIC receives the packet, send it to the XDP application. If the destination was XDP, it do the packet processing, send packet back, works great, super fast, the same way as kernel bypass. Now let's imagine the destination was the application which was running on the same box. So in that case, XDP will pass the packet to the kernel. And because XDP is a part of the Linux kernel, they can coexist, and it's actually passing the packet, so there is no additional copy involved. So XDP pass packet to the kernel writes to the application do its things, write back to the kernel, but now kernel have full access to the network interface card. And on the way back, it completely bypassed the XDP layer, so it can get all the benefits of the hardware offloading. So if we will look to the topology which we had before, when we were running Shift on the dedicated servers, we were doing this because we have seen the CPU inefficiency. And if you, for example, running the Edge cluster with 100 servers, only 10 of them are receiving all the ingress traffic and do the initial firewalling. So they could easily become the bottleneck. But now, with the new forwarding plane, all this CPU-related issue just went away. And this allows us to collocate Shift and Proxygen on the same box. So instead of 10% of the box which were handling ingress traffic before, today we can handle this ingress everywhere. And this greatly increases our ability to absorb any spikes in traffic. So let's talk about a little bit how future could look like. If you think about layer 4 load balancer or any networking gear, usually you can divide it into two big chunks. One of them is forwarding plane, one of them is control plane. Forwarding plane is responsible for the actual packet forwarding, and control plane is mostly responsible for the programming of the forwarding plane. Forwarding plane, like if you have a router, basically you need just to send packet from one interface to another. So for all of us, the forwarding plane could be the same. But control plane is actually really domain specific. For example, some people prefer to use gRPC for their PS. We at Facebook prefer to use Drift. Some other people are using HTTP REST. Or, for example, for the configuration part, some people prefer to use Zookeeper, other people prefer to use etcd, other people prefer to use the just plain files. But if you look into the forwarding plane, which stays more or less the same for everyone, it's actually not just the forwarding plane, but it's actually small shim layer of API on top of the forwarding plane, which allow you to communicate with it. So here at Facebook, we do really believe in collaboration. So we think like that together with community, we can build even better software. And that's why today we are open sourcing our forwarding plane, and you can download this from the GitHub. Sorry.
Thanks very much, Nikita.
Thank you.
Do you have any questions? Go to the front.
So how does it compare with OVS in this forwarding plane?
How does it compare with OVS, the forwarding plane?
So OVS is inside the kernel. So it's much slower compared to ours. And OVS, it's a virtual switch. This forwarding plane was built especially for the load balancing.
You got a question in the front, Mike?
So you said you can do non-equal load balancing, right? Can you
Yes.
also do some sort of affinity, like source IP affinity or something when you load balance? Or is it always like hash on the 5 tuple?
Can you elaborate on like what do you mean by that?
So what if my application requires to maintain source affinity, right? Like I want traffic from a particular source IP to always go to the same app server in the background.
So to be able to pick up the destination, we're taking the hash of 5 tuple, but like through the special knobs, we can say like instead of using source IP and source port, use just the source IP for the hashing. So all the packets from the same source will always go to the same backend.
So you can do that.
So yeah, you can do that.
Thanks.
In the back?
This is really awesome. Thank you so much for open sourcing up, and I'm gonna check that out after this. So this API, is that based on the eBPF and XDP or something?
So forwarding plane is based on the BPF and XDP. API is a C++ library which allows you to communicate with the XDP layer. And there is few examples where like service based on the gRPC and Thrift built on top of this API. But yeah, what we are open sourcing is C++ library in the user space, which allow you to program the XDP forwarding plane inside the kernel.
Awesome. Great. Thank you.
Go ahead.
Hi. So my question is more to do with when you receive a packet in your data path, right?
Mm-hmm.
So you saw you showed this diagram with the XDP and then the kernel on top, right?
Mm-hmm.
So are all your forwarding systems built in and out the same NIC, or do you go past? So you go in and one and out the other one.
So yeah, this is in our topology we're using single NIC for everything. So this is load balancing on a stick, but we do believe that most of the companies which are using load balancing running is in more or less the same environment.
Oh, good. Thank you.
All right, I think we have time for one more question in the back.
Hey, great talk. In your ECMP rehashing slide, you assume modulo hashing. I just want to know your thoughts on using consistent hashing with upstream ECMP router.
So what you're talking about, that some networking gear can implement the consistent hash?
Right, like many commercial
So
routers.
yeah, there was a couple of talks, mostly from the Fastly, where they can show you that, first of all, like, yeah, there is some consistent hashing in ASICs, but usually they have like small amount of buckets. And the second issue that it's not uniformly distributed. So what they have seen is that some of the next hops are more preferred compared to the others. So it's not as great as it could be. And here in software, our implementation is much more uniform, and yeah, it works just better. And we have like much more buckets.
Sure. Thank you.
Awesome. Thank you very much, Nikita.
Thank you.
Big round of applause.